This video is to introduce you to the concept of specific heat capacity and later on to the study of calorimetry. But before you move forward, I'd like you to think about being at the beach on a hot summer day, 75 degrees outside. You're walking towards the water and it hurts your feet to walk on that hot sand. As soon as you enter the water, though, your feet feel so much better. So hypothesize why you think that the sand at the beach is so much hotter than the water, knowing what you know now about heat transfer and different types of substances. So you may have guessed this, but maybe not. The reason why the water seems so much cooler than the sand is because the specific heat of the water is much higher. And that means it takes a lot more energy to heat up 1 kilogram of that water than it does 1 kilogram of the sand. From that, we can get the definition of specific heat capacity. Its symbol is C sub P. And the definition is the amount of thermal energy that is needed to heat 1 kilogram of a substance 1 degree Celsius or 1 Kelvin, assuming that pressure and volume are constant. I'm also going to let you know that in chemistry, if you're going on to IB chemistry next year, it's possible that specific heat is going to be introduced to you with a little lowercase s instead of C sub P. So know that if you see that in any problems that you're going to encounter in this chapter, little s and C sub P mean the exact same thing. So how do we get the amount of heat transferred to any object if we know an object's specific heat? The amount of heat transferred to a substance, which is capital Q, is going to be equal to the mass of that substance in kilograms times the specific heat capacity of that substance in joules per kilogram Celsius or joules per kilogram Kelvin times the change in heat. So this is the formula that allows us to calculate how much heat is going to be given by a certain mass of a substance that's changed a certain number of degrees, knowing its specific heat capacity. I would pause the video at this point, write that down in your journal because you're going to use that later on. So here is a table of specific heat capacities. No, you do not have to write these down in your journal, but these are going to be literature values given to you or you're going to find in the course of doing these specific heat and calorimetry problems. So our original question at the beginning of this video was, why is it that your feet feel so much hotter on the sand than in the water? Well, let's take a look at these specific heats values that are on this table. You see here's seawater, and seawater has a specific heat capacity of 3,900 joules for every kilogram of seawater to raise it 1 Kelvin. Here's sand up here, which has a specific heat capacity of 800 joules to raise 1 kilogram of the sand 1 degree Kelvin. So you'll see that it takes less energy to heat up the sand than it will the seawater. The lower the specific heat, the hotter something will get with the least amount of energy put in. So the next piece of this video is to show you how we calculate the heat transfer between two objects. In order to study heat transfer, we use a special device, and that device is called a calorimeter. And you'll notice here that the prefix calorie kind of sounds like calories that we find on the back of our food labels, because calorie is another way to measure energy. So it's the study of the transfer of energy, prefix calorie meaning energy. A calorimeter is an insulated container that can be used to measure the amount of heat transferred between two substances. In our case, what we're going to study is the transfer between metal to water. So you're going to design a coffee cup calorimeter on Wednesday. We're going to begin in lab on Wednesday, where you're going to figure out the identities of metals by calculating their specific heat. And you're going to design a calorimeter out of a coffee cup. Now you can use simple styrofoam cups, or maybe you can get fancy and use an insulated cup from your house. We'll talk about that a little bit later on. Before we move forward, I'm going to go back to my specific heat values here. You may remember in our power lab that 1 kilocalorie took up 4,186 joules. And if you take a look at the specific heat of water here, guess what? That's why we get the kilocalorie, because the kilocalorie is going to be the specific heat of water at standard temperature and pressure. So here's a simple coffee cup calorimeter. The secret here is that the outside of the cup has to be as insulated as possible. The more insulated your coffee cup is, the less heat will be released to the surroundings, the more precise you can measure the heat transfer between the metal and the water. You're going to have a thermometer. You're going to have a lid so the heat doesn't leave to the surroundings. You're going to know how much water you put into the calorimeter. And it's really handy to know that 1 milliliter of water is the same as 1 gram of water. You're going to have a hot piece of metal that you're going to put in there that you're also going to know its mass. And the only thing missing from this diagram is a hole in the top where you're going to put a stirring rod. And the reason for the stirring rod is so that you can make the heat transfer to the whole amount of water quicker. So this is a simplistic design for a coffee cup calorimeter. Keep that in the back of your mind, because you and your team are going to design one on Wednesday, and you are going to design it so that you will lose as little heat to the surroundings as possible. So in calorimetry, the study of heat transfer, what we do is we measure the amount of heat that's transferred to water. And we use water because it's the most common substance, and it has a high specific heat. If we have a perfectly insulated system and we adhere to the law of conservation of energy, the amount of heat gained by the water inside the coffee cup should be the same as the heat lost by the substance, in this case the metal. So the heat gained by the water will be the heat lost by the substance. Filling in the specific heat equation we saw at the beginning of this video, we will see that the mass of the water multiplied by the specific heat of the water multiplied by the change in temperature of the water will equal the equal and opposite of the mass of the substance, in this case the metal, the specific heat of the substance, and the change in temperature of the substance. Now, it's also interesting to note that if we're dealing with small amounts of water and small masses of metals, that these masses will probably be in grams, and therefore your specific heat of water will be 4.186 joules per gram for every degree Celsius. I just moved the decimal point over for the specific heat of water 3 places to the left. Okay, let's see how one of these problems works. So a piece of metal weighing 59.07 grams, that's going to be my mass of my metal, was heated to 100 degrees Celsius. That's going to be the initial temperature of the metal. And then put into 100 milliliters of water. I know that's the same as 100 grams of water. So that's going to be the mass of the water. The water was initially at 23.7. So that's the initial temperature of the water. The metal and the water were allowed to come to an equilibrium temperature, determined to be 27.8. So that's going to be the final temperature of both the water and the final temperature of the metal, both. And I'll write that clearer down below. So assuming no heat's lost to the environment, you built the perfect calorimeter, calculate the specific heat of the metal. So here's what we're going to do. I made this little table where I'm going to fill out the variables that I know. I know I want to find the specific heat of the metal. I know that the water's specific heat, and I'm going to use grams here because the mass of the metal is in grams. It's going to be 4.184 joules per gram degrees Celsius. Change in temperature of the metal. I started at 100 and I ended up at 27.8. So I'm going to say 27.8 minus 100. And this temperature change should be negative because the temperature of the metal goes down when I put it into the cool water. And I will find that that's going to be negative 72 degrees Celsius. The temperature change of the water, the final temperature is 27.8. The initial temperature was 23.7. So the temperature here should be positive because it's going up, and that should be 4.1 degrees Celsius. I know the mass of my metal is going to be the 59.047. And I know the mass of my water, which is going to be the milliliters of water, of 100 grams, 100.0 grams. So, 0.0 grams. What I'm going to do now is, since I realize the only information that I'm missing is the specific heat of the metal, I'm going to rearrange this equation to isolate the specific heat of the substance, which is the specific heat of the metal. So when I rearrange this to isolate the specific heat of the substance, I will end up with the following. No. So we're back, and what you see now is the equation rearranged to isolate the specific heat of the substance. So now I am ready to fill in my numbers, my measurements. Mass of the water is 100.0. Specific heat of water, again, I'm using the version that's grams, 4.186. Change in temperature of the water was going to be the 4.1 degrees Celsius, all over minus. Mass of the metal was going to be the 59.047. And the change in temperature of the metal was going to be negative . So here is the equation with all of the numbers filled in. I notice here, it's a real good thing that the change in temperature of the metal was negative, so that cancels out this negative sign, and I will find out that my final specific heat is 0.402. 5, and if I need to find my significant figures, I'm going to scroll back up here. And all my measurements, my lowest number of sig figs is with the temperature of 3. So I'm going to call this 4.03 joules per gram degrees Celsius. Now, what does that exactly mean? If I go back and take a look at my specific heat table, and I change that specific heat from joules per gram to joules per kilogram, I'll be about 403 joules per kilogram, which is about up here, somewhere in between iron, steel, and copper. So it's some alloy or some homogeneous mixture of metals that contains copper, iron, and steel. So about right there like that. Well, hoping that the last part of this video is not too jumpy, what I'd like you to try now is the problems page 316, numbers 1 through 4. If the video became too jumpy around minute 15, absolutely look at the example problem on page 315 of the book. Pretty much talks you through the exact same thing, except that example problem asks you to find the temperature, the final temperature of the metal. All right, good luck.